Okay, this is chapter 16, problems, problem set. So here we go. Okay, so the first thing we're going to do here is we're looking at the difference in the reactivity of benzene under these conditions compared to an alkene. So here you have a regular alkene with potassium permanganate and water, and it's cold. So this is mild oxidation. And if you remember, you get cis dihydroxylation. So we make the cis diol. And if you come down here with benzene and permanganate, the same conditions with the benzene ring, it is no reaction. Okay, and then you come up here to the bromination. And back in the day, before NMR, the way scientists determined whether something had a double bond was using colored oxidizing reagents, such as permanganate, which is purple, and in the presence of an alkene, it goes clear. And bromine is orange. So in the presence of an alkene, it goes clear. So what happens here, you get this bromonium intermediate, and then the bromide will nucleophilically open up that three-membered ring, and this forms an anti-bromination where the bromine comes from the top side and there we go. Now, if you do the same conditions with bromine and benzene, you get no reaction. Benzene is interesting in that it undergoes nucleophilic aromatic substitution, and this will be a chapter, next chapter, in chapter 17, we'll talk about the reactions of benzene. But if you want to brominate the ring, these are the conditions, and you just get one bromination under these conditions. Now, this problem is about the molar heats of hydrogenation. And molar heats of hydrogenation determine the stability of alkenes and other unconjugated systems. Well, conjugated systems. So, an example is 1,3-cyclohexadiene. So 1,2,3-cyclohexadiene. And a hydrogenation reaction would be, oh, so this should be hydrogenation. So you're adding hydrogen across the double bond. So hydrogen, usually palladium or platinum. And what happens then, you take it down to the alkane. And then you measure the amount of delta H heat given, enthalpy given off. And in this case, it's negative 232 kilojoules per mole. You can look that up in your reading. Now, if you look at benzene, you do the same reaction with hydrogen, pretty much palladium. Take it down to the alkane. You see that it is negative 208 kilojoules per mole. The predicted value, based on the added alkene should be something like negative 359 kilojoules per mole. It should go up. And in fact, it is actually less than the diene. And the reason for this is resonance. This is an aromatic compound. And that extra resonance that you get from an aromatic compound is the stability. And it's seen in the molar heats of hydrogenation. What is an aniline? Annuline. Okay, an annuline is cyclic hydrocarbons, so that's CHs, with alternating single and double bonds. So if we were to draw 8-annuline, then we have and I can do better than that. I'm basically drawing a stop sign. Okay, and we have 8. 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6, 7, 8. This would be 8-annuline. Is this structure aromatic? And we go on to talk about aromatic systems and the requirements. So basically, when you check for aromaticity in this compound, you have to check, is it cyclic? The answer is yes here. What about each atom, the hybridization? Is each atom sp2 hybridized? So let's check that. This one's sp2, 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 sp2. Yes. And because of this, you know that it's either going to be aromatic or anti-aromatic. Okay, it's going to be one or the other. It is not going to be non-aromatic. If it had an sp3 carbon, or if it was not cyclic, then it could be non-aromatic. Now what you do is to decipher between these two, you count the number of pi electrons, and you see if it fits the aromatic, this is Huckel's rule, of 2n plus 6, or just 2n. And n has to be an integer, 0, 1, 2, 3. It cannot be a half number. So when we do this, how many pi electrons do we have? We have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 pi electrons. And so if you see, obviously, 2n equals 8. Oh, I'm sorry. That should be 4n. I wonder if I can erase that. Yeah. Okay. I'm a little slow today. 4n plus 2 or 4n. Okay, so make that correction. So then the question is 4n equals 8. Basically, n equals 2. 4n plus 2 equals 8. You'll see that 4n equals 8 minus 2. 4n equals 6 divided by 4. This is going to give you a fraction. Okay? So this does not apply here. And this compound would be considered anti-aromatic. So it would be not aromatic. Okay, the next one is the Polygon rule. So the Polygon rule predicts the molecular orbital energy diagram for different cyclic compounds. So the way you do this is, so if you look at cyclooctatetracene, it has 8 carbons, and then it's tetracene. So 1, 2, 3, 4, 5, 6, 7, 8. This is cyclooctatetracene. There's 4 double bonds. And you basically have an increasing energy diagram. And then this is just your coordinates on the bottom. And what you do with the polygon rule, you have to turn it on a point. So if we turn this on a point, what does that look like? This is actually kind of hard to draw, but I'm going to these two on the same point, these two, same point, these two on the same point. So I'm going to turn that on its vertices. So let's try to draw that on its vertices. So there's that. And then so we got 1, 2, 3, 4, 5, 6, 7, and then go to the last one, 8. So you see how that's kind of funky? I mean, like if you do like cyclobutadiene, then that's a little bit easier, right? Because you're making a diamond. And then those are your energy molecular orbital places where you can play in your electrons. So, but here, this is a certain energy. This is your energy, so this is lower energy. Then you draw these lines here, and this is where you're going to fill in your pi electrons. And the key is these are degenerate orbitals. They have the same energy, degenerate energy, because they're on the same level. Now, how many pi, and then you count your number of pi electrons. Number of pi electrons in this system, 1, 2, 3, 4, 5, 6, 7, 8. 8 pi electrons. And then you fill the pi electrons from the lower energy to the higher. Now, one other thing you need to note is 1, 2, 3, 1, 2, 3. Right here, these are your non-bonding. And that's important. So when you split the molecule, just like here with cyclobutadiene, this would be your non-bonding. That's your non-bonding line. So anything on that line and above that line would make the molecule unstable. Now you fill in your, in this case, 8 pi electrons. So 1, 2, 3, 4, 5, 6, 7, 8. And because of the the Pauli exclusion rule and Hund's rule, you basically have to put these electrons in the degenerate orbital, and you got to fill up all the orbitals before you can put 2 electrons in one orbital. So these have, you can see now you have single unpaired electrons in these orbitals. This is very destabilizing. So that's really what makes it anti-aromatic. So if you remember in class, I said the difference in aromatic and anti-aromatic. Anti-aromatic, the cyclic structure, resonance structure, actually destabilizes this molecule. And for something to be aromatic, that cyclic resonance structure needs to be more stabilizing. And just to finish up this cyclobutadiene, we got 1, 2, 3, 4 pi electrons. So 1, 2, 3, 4. So once again, you have electrons on that non-bonding orbital. For kicks, let's just do benzene here. Okay, benzene's kind of easier for me to draw because I always draw benzene with its vertices. Okay, so this is your energy, and then you draw in 1, 2, 3, 4, 5, 6. And then halfway through, this would be your non-bonding line. Because remember, this is bonding. We have 3 orbitals bonding, and then we have 3 orbitals anti-bonding. You have to have equal number of bonding and anti-bonding pi orbitals. Now, benzene has 1, 2, 3, 4, 5, 6. It has 6 pi electrons. So then we fill them up. 1, 2, 3, 4, 5, 6. So we have 6, and they're all in the bonding. So this makes it aromatic, and it is stabilizing. Okay, the next one we have is the 4 criteria for compounds to be classified as aromatic compounds. So 1, the structure, this is straight out of your book, needs to be cyclic, and it needs to contain conjugated pi bonds. The second criteria, each atom in the ring must have unhybridized p orbital. They're usually sp2. They can be an sp, okay, but they're usually sp2. 3, unhybridized p orbitals must overlap to form a continuous ring of parallel orbitals. So this basically needs to be planar. Now, if you get into some of your larger ring systems, you'll find that due to the ring is not so rigid, so it can move into these non-planar. And even though it's cyclic, number 1 and number 2 fit the aromatic compound description, number 3 is failed because it can actually be flexible and conform out of this planar, which would violate number 3. And then we have number 4, which is the delocalization of the pi electrons over the ring must lower the electronic energy. And this is what fails for a compound that's anti-aromatic, number 4. So which of the criteria is not met when it's classified as anti-aromatic? That would be number 4. Which of the 4 criteria, when not met, makes the compound classified as non-aromatic? 3 would be one of them. 2 would be one of them, and 1. So 1, 2, and 3. 1, 2, and 3. Usually it's going to be 2 that you're going to classify as non-aromatic. What is Heukel's rule? Okay, Heukel's rule is hold on just a second. Okay. You have to count up the number of pi electrons in the cyclic system. And if it meets the 4n plus 2, the system is aromatic. And if it fits 4n, the system is anti-aromatic. And n would then be an integer. And it's commonly either 0, 1, 2, or 3. Okay, so number 5, 6. Number 6. This is the naming. You will be required to name compounds. So let's just start with our first name here, A. So this is toluene right here. And so meta Just real quick, I'll show you. This position is ortho. This position is meta. And this position is para. So when you have a meta-methyl-toluene, the methyl group then would go here. That's meta-methyl-toluene. Okay, the next one is dichlorobenzene. So this is benzene. And dichlorobenzene then would be where you just pick somewhere to put a chloro. And you use the ortho-meta-para substituent nomenclature when you have a disubstituted. So disubstituted aromatic compound. So ortho-dichlorobenzene then would be this compound. Okay, you've seen this structure before. Meta, chloro, perbenzoic acid. Perbenzoic acid then would have 3 oxygens. And we also call that MCPBA. Okay, D, nitrophenol. So just so you know, this is phenol. And you're expected to know that. That's phenol. And then paranitrophenol then would be para, this position, and nitro, NO2. That's paranitrophenol. Okay, we just did phenol here. We've done toluene. This is toluene here. Aniline, you need to know aniline. There's basically 4 of them. There's benzene, there's phenol, there's toluene, and then aniline has an NH2. This is aniline. Methoxybenzene. There's no number there. So it's just OCH3. Methoxybenzene. Tert-butylbenzene. So you just put the tert-butyl group on the benzene. Nitrobenzene. Just put a nitro group. You don't have to worry about disubstituted. Now we have 2-methylbenzoic acid. And we did perbenzoic acid, so this would be benzoic acid, which is 2 oxygens. And we have 2, so that's 1, 2. 2-methyl. That would also be called orthomethyl-benzoic acid. Nitroaniline. Nitroaniline, so we draw aniline. And we don't, see, it's a 4. So that would be 1, 2, 3, 4. That's also para-nitroaniline. Then we have para-aminobenzoic acid. So let's draw the benzoic acid. That's benzoic acid. So it has the benzene ring. And then para-amino. So 1, 2, 3, 4 right here. Amino is just NH2. That's para-amino benzoic acid. And then we have para-nitroaniline. So here's aniline, and then para-nitro, NO2. Para-nitroaniline. Okay, now we're supposed to name them. So here, if you see that, you can see that this is phenol. And this is ortho. This is the meta position. And this is the para position. So I would name this meta-chlorophenol. Another way you could name it is 2-chlorophenol. Here, if you see this is toluene. You pick one of the 4, okay? So you either have benzene. If you have a methyl group, you tend to call that toluene. If you have a phenol group, you call that phenol. And if you have an NH2, that's aniline. You have something like this. This is benzoic acid. So here, this is toluene. So the base is going to be toluene. And here you would do 2, 3, 4, 6 trinitro-toluene. That's TNT, dynamite. Okay, this group here, that's your, see how you have this oxygen, that's perbenzoic acid. That's your ortho, that's your meta. So this is meta, which you can just write M, dash chloro, perbenzoic acid. Now this one, you might not recognize it, but it's in your cereals and a lot of your food. That's BHT. And the T stands for toluene. So if you find the base there, this is toluene. And the H stands for hydroxy. And the B is butylated. So this would be, if you're going to take the base as toluene, then that's going to be 1, 2, 3, 4, 5, 6. And so you would write toluene. And then you would have 4-hydroxy 3, 5 ditert butyl toluene. And that's BHT. Okay, on this problem, this is a little more challenging. What happens here is if you can deprotonate, so a base has its lone pairs, and whenever you're looking at compounds to figure out what's acidic, then you got to have a base. And a base will deprotonate, and it will always deprotonate the most acidic proton. So you look for those, and the most acidic proton in these systems is if you can take away a hydrogen, if you can remove that proton H+, it will leave the 2 electrons behind that make up the carbon-hydrogen bond. And so when the base comes along and takes away the proton and leaves the carbon with those 2 electrons, and the base gets the hydrogen, then what you're left over doesn't make the system aromatic. If it actually makes the system aromatic, that's going to make that proton a very acidic proton. So the first, third, and fourth structure can lose a hydrogen, a proton, from an sp3 to generate more resonance. Okay, so you can lose, there's an sp3 and can lose a hydrogen. This one right here is an sp3 and can lose a hydrogen, and it can develop more resonance. And right here, sp3 can lose a hydrogen. But none of these actually make the ring system aromatic, except for the second one. So let's look at the second one. And we will put the hydrogens on here. So this has 1, 2, 3, 4, 1, 2, 3. There's a hydrogen here. 1, 2, 3, 4. Hydrogen here, and a hydrogen here. Okay, so when you're doing these, you want to show your hydrogens. Okay, the base then comes and will deprotonate. So let's say it deprotonates this hydrogen here. Now, that hydrogen takes those electrons and puts them right there. And when that happens, these electrons then get pushed onto that carbon. So let's draw that reaction. So let's draw our base with our hydrogen, and then let's redraw CH3, CH3, CH, and we have those electrons there, and then those electrons went to this carbon. Now, count how many pi, so we do have, let's check this system out to make sure it's aromatic. Is it cyclic? Yes. Is every carbon, every atom sp2 in the ring? One, that's an sp2, that's an sp2, 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 sp2. Yes. Okay, so now, what's the number of pi electrons? It's got to do Huckel's rule. Is it 4n plus 2? And then does it fit the 4n? So the number of pi electrons, we have 1, 2, 3, 4, 5, 6. We have 6 pi electrons. And I think by now you know that 4n plus 2, where n equals 1, is 6. So that would be aromatic. And that makes this proton, that's a driving force, to be aromatic. It makes it very acidic. Okay, the next problems are classifying compounds as aromatic, anti-aromatic, or non-aromatic. So the first, what we're going to do is we're going to look, and you see that these are all rings, okay? So that's number one criteria met. What we're going to basically do is we're going to check every atom to make sure it's sp2. Like I said, it could be sp3, but basically, it could be sp. Usually they're sp2. If it's sp3, okay, we're going to say that is non-aromatic. So if there is a ring atom, I say atom because we also have oxygens, and we have nitrogens, and we have carbons. If it's an sp3, it's non-aromatic. And if it is sp2, and they're all sp2, then you're going to decide whether it's aromatic or anti-aromatic. And how we do that is we count the number of pi electrons, and then we fit this system, either 4n plus 2 or 4n, where n is either 0, 1, 2, or 3. Okay, so let's go on. The first one we have here, and you can see that this right here is an sp3. So that makes that one non. I'm just going to put N, O-N, non. Okay, here we have sp2, sp2, sp2. So they're all sp2. And now we count the number of electrons, pi electrons. We have 4 pi electrons, which makes it 4n plus 1. 4 times 1. This is anti. Okay, so that's anti. Here we have, they're all sp2. And we have 2 pi electrons. And so if n equals 0, then 4n plus 2 equals 2. So this would be aromatic. Okay, so that's an aromatic system. Okay, going to the next one. This is, now I like to put the lone pairs in there because it helps to count. So we have sp2, sp2, sp2. So they're all sp2. So you're looking at, is this aromatic or not? You count the pi electrons. Now, there's 2. There's 2. There's 2. And then you go ahead and give, if that center can contribute, that oxygen can contribute to lone pairs to the pi system, it will. Okay? And the reason why is because resonance stability for aromatic systems is such a strong energetic driving force. So In this situation, that would be a 6 pi electron system, and we know that 6 pi meets the 4n plus 2. So B, that's aromatic for the first structure. Okay, so let's go ahead and put in the lone pairs for the next one, for the nitrogen. And we have each atom is sp2, hybridized. And then you could count 1, 2, 3, 4, 5, 6. So that is also aromatic, because it meets the 4n plus 2. Okay, our next system here, this is THF, tetrahydrofuran. These are all sp3 carbons, so that is non. So that's non-aromatic. Okay, so what do we have here? We have, on the next one, we have every atom is sp2, and the lone pairs are already drawn in for us here. Okay, and now we count the pi electrons, so we have 1, 2, 3, 4, 5, 6, and therefore it is aromatic. Okay, so let's look at the next system here. Each atom is sp2, and now we count the pi electrons. And nitrogen doesn't have a lone pair. You see this plus charge with 2 hydrogens? It has no available lone pair. So here we just have 4 pi electrons, and 4, that's where n equals 1. So 4n would be anti. So this is anti-aromatic. Okay, let's go on to C. C, you can see right here, that center is an sp3. So that's going to be non-aromatic for the first one. Okay, the next one, every atom is sp2. Okay, so they're all sp2. And now we count the pi electrons. 1, 2, 3, 4, 5, 6. 6 pi. So the 6 pi makes that aromatic. Okay, because it's the 4n plus 2. Okay, the next one, all atoms are sp2, because that's a carbocation, but we only have 1, 2, 3, 4 pi electrons. So that's going to be anti-aromatic. 4 pi electrons. That's n equals 1. Okay, the next system, boron is sp2, so they're all sp2. And once again, boron does not have any lone pairs. And so that system only has 4 pi electrons, which makes it anti-aromatic. Okay. Now we are on D, part D. Okay, so D, let's go ahead and draw in our lone pairs. Nitrogen forms 3 bonds and 1 lone pair. All atoms are sp2, hybridized, and then you can see that we have 1, 2, 3, 4, 5, 6 pi electrons, so that's going to be aromatic. The same here. This compound here, all sp2, and there's 1, 2, 3, 4, 5, 6 pi electrons. That's going to be aromatic. The next one, we got nitrogen with 3 bonds. Let's draw in our lone pair. Do you see that is an sp3? That's going to be a non-aromatic. So non-aromatic. And the next compound here, we have everything is sp2. Every atom is sp2. We don't have lone pairs on nitrogen because it's protonated. And we do have sp2. We have 6 pi electrons. And so that's aromatic. That's part of that, when we do PCC, pyridinium, that's your pyridinium ion. Okay, now, dealing with E, You have to actually know something about this structure. So I wouldn't expect you to know anything about the structures without reading on page 724. So if you read on 724, you can learn that some of these are not, because they're not so rigid, you could see that they might not be able to adopt a planar system. But here, if you could just see that this is all, all of these have sp2 centers, and if you draw the resonance structures, you would be able to see this. You count the pi electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 pi electrons, and you see that that actually meets the 4n, because n equals 3 equals 12. So 4n is anti. So for E, that would be anti-aromatic. Okay, this system here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 pi electrons, and that would then be 4n plus 2 equals 10, 4n equals 8, n equals 2. So that would be aromatic. And then the last one we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 pi electrons. So it's also aromatic, just like the previous one. All right, this question is about classifying each nitrogen atom as strongly basic or weakly basic, according to its availability of lone pairs. So the first thing you want to do is you want to put in the lone pairs on the nitrogen. So nitrogen has 3 bonds and 1 lone pair. So we can do this for each one. And then you want to put in for oxygen. So it's always good to put in the lone pairs. I'm just going to do that right off the bat here. Okay, and now we're going to classify each nitrogen atom. So basically, to be strongly basic, what are you looking for? So to be a strongly basic nitrogen, it has to have an sp2 lone pair. Okay? If its lone pair is in an unhybridized p orbital that is used being used for aromaticity, okay, so meaning it's delocalized into the ring system, then it's not available to go and be a base. And to be a base, it needs to take its lone pairs and it needs to go to another compound, and it needs to deprotonate that, and it needs to be able to form that bond and take the hydrogen away. And electrons that are in the unhybridized p orbital are not going to leave the energetics of being delocalized into the ring system to go and get a hydrogen. Okay, it's like you picking up a penny. Sometimes you don't pick up a penny, but if you got a silver dollar, then you might bend over and you pick up the silver dollar, okay, because it's worth your energy of bending down and picking it up. And sometimes a penny to you might not be worth your effort. Okay, so energetically, these electrons that are available to pick up a hydrogen have to be in an sp2. So we have to look at the aromatic system and then decide. So you look at this compound here, and they're all sp2, and so let's look at the first one. The first one has, so what electrons are contributing to the pi system? These are, and these are, okay? because each atom has to contribute some electrons there. And so these electrons are unhybridized. They're in the unhybridized P. As you can see, all three of these attachments, these atoms that are attached to this nitrogen, are being used for an sp2. When you have an sp2, how many is that? That's basically this little wiffle ball orbitals, and there's 3 of them. So in sp2 system, you have 3 things that can bond. And so those lone pairs have to be in an unhybridized P. And that means they're going to be weakly, classified as weakly basic. Okay, so you take, now however, these electrons are not needed, and that's going to be strongly basic. Now, if you notice, if the nitrogen has a double bond to it, then the lone pairs on that nitrogen typically are strongly basic. If the nitrogen has a single bond, then those electrons end up being unhybridized. Let's see if you can look for this. This one here, this one's going to be strongly basic. Okay, these on this next compound are strongly basic. And that is because those electrons are in an unhybridized p orbital. Actually, no, that would be sp3. Unhybridized p orbital. That would actually be in a 1, 2, 3, 4, an sp3 orbital. They're in sp3. sp3 orbital pi electrons are excellent. They're excellent bases. Okay? So those lone pairs will definitely, on the nitrogen, will be strongly basic. Those electrons are in sp3. Okay, so looking at this structure here, what electrons are contributing to the aromaticity pi electron system? Those 2 and those 2 in the ring. And then oxygen's contributing 2. So that means these electrons here are available. And this availability then makes this a strongly basic nitrogen. Okay, so that's an sp2 lone pair. That's sp2. sp2 are strongly basic. They're in the hybridized system, hybridized p orbitals. Okay, now looking at this compound here, the next one, which electrons are in the system. So there's 1, 2. There's 3, 4, and then this would be 5, 6. Okay, so both these electrons then are in the hybridized system, and they're sp2. So they're both going to be strongly basic. And then, of course, this one here is going to be weakly basic. So that one is weakly basic, and these 2 are strongly basic, because those are in hybridized p orbital. And then looking at this here, this is an sp3, and sp3 lone pairs then would be strongly basic. Okay, so this is the last problem in this set. And one of the key things here with these charged ring systems is drawing resonance structures and figuring out also whether these resonance structures contribute to the aromatic. So the first thing you want to do is make sure, like, they're all sp2 atoms. So as you see, in this case, it is. And then we draw the electrons here, and if you draw the resonance structure with the resonance arrow, then it's kind of like a push-pull. All these electrons can go into the system. So those electrons go here, and those electrons go towards the carbocation. And then we redraw, and as you can see, now the plus charge is on oxygen, and the cation on the carbon, like I said, indicates an empty p orbital. So the 2 pi bonds plus a pair of electrons make a 6 pi electron system. So this would be aromatic. Okay, so the next compound here, we'll draw this one out. With its lone pairs for oxygen. And all of the atoms are sp2. And so the thing here to do is to draw the resonance structures. And so the electrons here would go here, and they would go here, and then those electrons go there, and then you redraw. And that gives the oxygen positive charge, and this oxygen is a negative charge. And that negative positive charge cancels out to make 0. And this would be considered aromatic. The resonance form shows a push-pull of electrons from one oxygen to the other. This makes the cyclic pi system with the electrons. Okay, let's redraw this compound and check out any resonance structures here. So this compound, every atom is sp2, and now we're going to draw, let's see what kind of resonance structures we can draw. So these electrons go here, these electrons go there, these electrons go here, and electrons go there, and we redraw this. And the positive and the negative cancel out to make a neutral molecule. And so that would be a realistic resonance structure, and every atom is sp2 and 6 pi electrons, so that would make that aromatic. Okay, doing the next compound, we have a carbocation and a carbonyl. So every atom is sp2, and in this situation, we have these electrons can go here, but in that case, it just puts the positive on this carbon and makes there's no way to really get those electrons in the ring, so this would have only 4 pi electrons, which would make it anti-aromatic. So that would be anti-aromatic because it is the 4n, where n equals 1. And that would be anti-aromatic. Now let's look at this compound though. So we look at the anion. And we see that it has, everything's sp2, but now it has 6 pi electrons in the pi system, and that could do a resonance structure that looks familiar to you here. Rather than have the negative on the carbon, we have the negative, and this is a phenoxide. And this is definitely aromatic. There would be the resonance structure there. So that one's aromatic. All right, so then the next compound we have is with the nitrogen. And we got a positive carbocation in there. And we have electrons here. And we want to draw the resonance structure for this compound. Let's see. Let me look at it real quick. All right. So if these electrons go here and those electrons go there, what does that structure look like? And that's the pyridinium ion, and that is definitely aromatic. As you can see, it has 6 pi electrons. Everything's sp2. So that is aromatic. Okay, the next compound here with our lone pairs, the nitrogen and oxygen. And to draw a resonance structure of this compound, we would do such as that. And let's draw our resonance structure here. And the oxygen would have a negative charge. And so therefore that's aromatic, because every atom can be sp2, and we have 6 pi electrons. So that would be aromatic. Okay, so then our next compound is this compound here. So there's nitrogen, carbonyl, and that nitrogen in there, drawing our lone pairs. And so at this point, every atom is sp2. And when we draw a resonance structure, we got these lone pairs. We got nitrogen has a lone pair. So let's see, if we push those there, you can push those there. Sometimes you might have to draw more than one resonance structure. Let's see what that looks like. Redraw. There's your nitrogen there. Okay, so now you have your okay. 1, 2, 3. We'll just go ahead and put those there. Because they can move because they're in a pi system. And then we redraw this. As you can see, we do have, there we go, there's the plus and the minus, and the plus and the minus. Okay, so this is a resonance structure, and this is a resonance structure. And in this situation, this is a 6 pi electron system. Okay, and now we have this tropyline has lone pairs. Let's do this up here. And so we don't have to draw any resonance structures here. We just count how many pi electrons. So for this oxygen to be an sp2, that means one of these have to contribute to the pi system. So that's 1, 2, 3, 4, 5, 6, 7, 8. That's 8 pi electrons in that system. And that is 4n, where n equals 2. So that would be anti-aromatic. And then this last one, basically, it only has, these electrons cannot participate, so it has 4 pi electrons. Every atom's sp2, but you only have 4 pi electrons. That's 4n, where n equals 1. So that's anti-aromatic as well. Okay, toluene, this is toluene, reacts with bromine in the presence of light to give benzyl bromide. Proposed mechanism. Okay, so what we have here is we have bromine and H nu. So this will polarize and bromine will form a free radical. So you would generate 2 bromine radicals. And this would be a homolysis. And this is called initiation. And now we have a benzyl position. And benzyl positions react differently because of resonance. So this is propagation, and you're going to have, I think, 2 propagation steps. So basically you have your neutral benzyl toluene. You got your toluene, and it's reacting with your bromine radical. A lot of times you just draw the radical species. And the first thing it's going to do is it's going to abstract a proton or a hydrogen. You would call that a hydrogen. So this is going to go and take that hydrogen, and it's going to form a bond with that bromine, and then that carbon is going to take the electron, and this generates a new radical, and it's going to be a sp2 carbon radical, and now you have HBr. And then the second propagation step, you take your free radical, your carbon free radical, and this is where you're going to make your benzyl bromide product, because now it's going to react with another Br, and it's going to form that bond there. So we draw our product. And so when you draw this mechanism, you want to draw 2 propagation steps, and you want to make sure that you're regenerating the bromine radical to go and abstract another hydrogen off of the benzyl position of toluene. And that is how that reaction works. You need to be able to draw that mechanism, by the way. Okay, now, so here we have draw the products for the 2 reactions below. What is the name of the functional group and the products as a result of the reaction? What is the name of this reaction? Which of the following reactions will have the faster rate and give the better yield? Okay, so we have a benzyl bromide. That's how you classify that. So that is, it's an excellent SN2. Because if you notice, this carbon here is sp3, and it's stabilized because of the aromatic group. So now you have a strong base, or a good nucleophile, sodium methoxide. So what happens is sodium methoxide is going to do a backside SN2 tag. Bromine is a great leaving group. This is a great nucleophile. You've got basically a very reactive alkyl halide, and you're going to get OCH3. What is this functional group? It is an ether, and it's the Williamson ether synthesis. Okay, it's got an alkoxide with an alkyl halide to make an ether, Williamson ether synthesis. Here we have a primary alkyl halide, not a benzyl alkyl halide. And this comes in, does an SN2, and you get a ether. And this is also the Williamson ether synthesis. And the rate, the reaction that's going to go the fastest is the benzyl bromide. Benzyl bromide will have a better yield and a faster rate.